Welcome to this explainer. You know, your computer looks incredibly complex from the outside, but deep inside, it's really just simple switches turning on and off. In this explainer, you'll understand how a computer actually works, from binary numbers all the way up to the CPU. So let's dive into this. It's kind of crazy to think about, right? How does a complex machine run purely on ones and zeros? I mean, how do those simple digits translate into stunning 3D graphics, global internet routing, and massive algorithms? It feels a lot like magic, but actually, it's just pure, brilliant logic. Here's our roadmap for today. We'll be looking at analog versus digital signals, the binary number system, how logic gates make decisions, storing data with flip-flops, and finally, architecture and clock synchronization. Let's get right to it.
Section 1. Analog versus digital signals.
The absolute most crucial thing to wrap your head around here is that computers only understand digital signals. Out in the real world, we deal with analog signals, which you can picture as smooth, continuous sine waves. But digital systems? They hate ambiguity. They take that continuous wave and force it into discrete, strict steps, acting like a square wave. It's either a 0 or a 1, low or high, off or on.
Section 2. The binary number system. Because our hardware strictly relies on these two states, everything in a computer is stored in binary. It's a math system with just two digits, 0 for off and 1 for on. Take a look at this sequence, 10110101. To a computer, that specific string is the decimal number 181. But how does it actually know that?
Well, it works kind of like our everyday decimal system, just using powers of 2 instead of tens. So instead of a ones, tens, and hundreds place, binary uses 1, 2, 4, 8, 16, and so on. If you've got the sequence 1, 1, 0, 1, 1, you just add up the weights wherever a 1 is present. 16 plus 8 plus 2 plus 1, that's exactly 27. And since basic addition and subtraction rules apply across the board, the computer can use a single highly scalable hardware circuit to chew through massive amounts of math.
Section 3. Logic gates make decisions. Enter the logic gate. These are the absolute basic building blocks of digital circuits. The idea is elegantly simple. They take inputs and give an output. You feed it an electrical voltage, strictly on or off, and it spits out an answer based on a specific rule. Like a NOT gate, it just reverses the input. Put a 1 in, get a 0 out.
But things heat up when you add multiple inputs. We map these out using truth tables. Take the AND gate. It acts like a very strict bouncer. It requires both input A and input B to be a 1 in order to output a 1. If even a single input is a 0, the output is 0.
On the flip side, the OR gate is way more chill. It outputs a 1 if literally any input is on. We've also got gates like the XOR, which spits out a 1 only when inputs are different, and XNOR, which outputs a 1 when they're exactly the same. Now, engineers use a mathematical system called Boolean Algebra to handle all these variables. By applying simple rules like A plus A equals A, they can drastically reduce circuit complexity, saving tons of physical hardware space. But here is a real game changer. If you combine a NOT gate with an AND gate, you get a NAND gate. Combine NOT with OR, you get NOR. These two are called universal gates. Why? Because you can use them to build absolutely any logic circuit or implement any Boolean function without needing any other type of gate. It is literally a masterclass in engineering efficiency.
Section 4. Storing data with flip-flops.
Okay, so basic logic gates process things in the moment. But how does the computer actually remember anything? Well, that's where sequential circuits come in. By feeding an output back into the input, you create stable memory. We call this basic memory unit a flip-flop. A single flip-flop stores exactly one bit of data, a 0 or a 1, making it the fundamental foundation of computer storage.
Now imagine scaling that up. Group a bunch of flip-flops together and you get a register, which stores multiple bits at once. Keep grouping those registers, and suddenly you've built massive memory units, like your computer's RAM, which stores data right when the processor needs it.
Section 5. Architecture and clock synchronization.
Pack all these microscopic components onto a silicon chip, and you've got an integrated circuit. And the big boss of these circuits is the microprocessor, the literal brain of the computer. Inside a CPU, the arithmetic logic unit handles the math, the control unit runs the show, and registers hold temporary data.
Ultimately, the CPU processes everything using those exact logic gates we just talked about. And just to clarify a quick distinction, while a microprocessor is the brain and needs external memory to work, a microcontroller, like an Arduino, packs the processor, memory, and inputs all into one single all-in-one chip.
But hold on, if you have billions of logic gates pulsing on and off, how does it not instantly turn into electronic chaos? The secret sauce is the clock signal. The computer uses a master clock that sends out continuous square-wave timing pulses. This ensures every single gate and flip-flop synchronizes and changes state at the exact same moment. So when you buy a CPU that runs at 3 GHz, that literally means it is executing 3 billion perfectly synchronized cycles every single second.
Wow, what a journey. Let's summarize. Analog versus digital gives us our signal types. Binary is the underlying language of the computer. Logic gates handle the decision-making. Flip-flops provide the memory. The CPU manages the processing, and the clock signal keeps the timing absolutely flawless. Now you understand how a computer actually works from the inside. It's wild to think that the infinite complexity of our modern world still entirely boils down to simple digital switches. In the next explainer, we'll go deeper into real digital circuits. Until then, what do you think these simple binary switches will build next?